Welcome to OPM's InnoZone. My name is James Porteous, Director of Engineering for OPM. I'm joined today by Dr. Thomas Webster of Northeastern, and we're going to talk to you a little bit about PEKK polymer, 3D printing with PEKK polymer, how we manufacture medical devices, through that process, and some of the unique attributes of those devices. So just a little bit of background on the company. OPM was founded in 2000, really as a material technology company with a PEKK polymer focus. So we're a medical device OEM, contract manufacturer. We are ISO 1345 certified, FDA registered, all that fun stuff. Headquartered in Connecticut, USA, and we have about a 34,000 square foot facility here that we do all manufacturing and design and development activities. So our products today, all 3D printed implants on the market currently, 510K clearances for patient-specific cranial device, patient-specific facial device, a vertebral body replacement, and most recently a suture anchor system for rotator cuff repair. So those are all 3D printed with PEKK polymer. And just a little bit about PEKK polymer. It is a high-performance engineering polymer. So that really just means that it's very durable, very robust. It can withstand harsh conditions, high and low temperatures, corrosive environments. It's just very non-reactive. So good for high-demand applications, things like biomedical implants, automotive, aerospace, defense applications. As you would expect, it's fully biocompatible, so we've done all the testing at OPM to show that it's suitable for long-term implantation. And one of the unique properties of PEKK that kind of differentiates it from the other polymers in the polyketone family is the adhesion and wetting characteristics that it displays. So it's just very kind of sticky. It sticks to itself, it sticks to other substrates and other fillers. You can see in the picture here, PEKK on the right with some glass fiber filler, and it's just really, everything is stuck and well incorporated into that bulk matrix. So this is really kind of the property of PEKK that's enabling us to 3D print with it and use it in a layer by layer process where you really need good bond strength between those layers. So for 3D printing with PEKK, we use a laser sintering or laser melting process. So if you're familiar with this process, it basically starts out with a 3D CAD file that gets kind of cut into two-dimensional cross sections and uploaded to the printer. The printer is then lasing each 2D cross section in that bed of powder, and then additional powder is deposited on top, and that process continues until you have a three-dimensional part kind of built up in that bed space, really just fully melted and consolidated and floating in that bed of powder. So our process at OPM is build preparation. The printer does the manufacturing pretty much on its own once everything is uploaded. Once that process is complete and everything is cooled, we break out the implants and the parts from the part bed. It's really kind of like an archaeological dig. At that point, everything is floating within that bed of powder. We do inspection here, however they need to be inspected, and then they are shipped to the healthcare facility for surgery. One of the really unique properties of parts that are made through this process is the surface texture. So we refer to it as kind of a peak and pit-like structure on the surface, almost like a skin. It's not a porous material at all. It's just kind of a rough skin texture that's on the surface. And this is really, we're seeing being an enabler for many functional properties that we're going to talk about today, specifically bone on-growth to the surface and antibacterial characteristics. So we've studied the surface a lot. As a company, we really like to go in depth with science and look at the whys things are happening. So we were investigating this osteointegration potential of 3D printed PEKK, OsteoFab PEKK, and we performed an internal rabbit study just to see, okay, what's the performance of bone on growth of the material versus conventional materials like PEKK, which we know and continue to see today generate a non-integration with bone or a fibrous tissue response. So we did a 8 and 12-week time point study. We looked at smooth PEKK, roughened PEKK, as well as 3D printed OsteoFab PEKK. And these are the just quick summary of the results that we saw. Kind of a typical PEKK response here. These are cross sections of rods that were implanted into the medullary canal of rabbit. So you can see here the bone in kind of white and the implant surrounded in the middle. And on the right is the histology, kind of the confirmation of what we're seeing on the DSCM. So here you can really see that implant in brown just kind of surrounded by void space, really no bone contacting the surface. Typical type PEKK response. Even with the roughened grip blasted surface on PEKK, still not really any bone contact there, nothing really reaching out and grabbing onto the implant. Versus the OsteoFab PEKK response of bone really reaching out, challenge really with that gap still reaching out and integrating to the surface, getting into those grooves on the surface. And this is a pretty good representative picture here. Both at 8-week and 12-week time points, we really see, the capability for integration that OsteoFab PEKK has, and the ability to osteointegrate with host bone. So this is a pretty eye-opening property for us to see, and we did a lot of follow-up work with a bunch of different researchers, different universities. There's been many papers that have come out since we did our internal work that are really confirming this property and showing that 3D printed PEKK is capable of integrating with bone. Just quickly, this is one of the follow-up studies. It's a good representation of OsteoFab PEKK response versus smooth PEKK and also titanium coated PEKK, which is another kind of common material on the market today. So similar integration potential to titanium with the OsteoFab PEKK. You can see here with the rod on the right. This was a rod that was implanted in a sheet model and then pushed out, and the bone was so integrated to this rod that it just really pulled all the bone out with it. So this is really typical response to the material. One of the second unique surface properties of 3D printed PEKK is the bacterial inhibition characteristic. So we did some work back in 2017 with Dr. Webster, who is presenting here with me today. And we were able to demonstrate really increased bacterial adhesion to the surface of 3D printed PEKK versus smooth PEKK. So this was kind of, again, another eye-opening property for us that we wanted to delve further into and study further and understand the why. So this is kind of where Dr. Webster comes in, and we've been working with him for quite some time now, looking at mechanisms of these two properties and why they are what they are and how they're working. So with that, I'll turn it over to him.
Yeah, thank you, Jim, for that nice introduction about PEKK and how we've been collaborating with OPM to explore some more of its novel properties, as well as a why. Why does PEKK behave this way, improve bone growth, and inhibit bacteria functions? So Jim, if you want to go to the next slide. I'm at Northeastern University, as Jim mentioned, in chemical engineering. We have over a 25-year experience looking at novel materials in orthopedics, and that's how we got connected with OPM to do some studies on their materials. So next slide. Yeah, so this is just a description of some of our experience over that 25-year period, whether we have looked at 3D printed spinal implants or amputee devices, or in the bottom corner, looking at increasing bone growth on materials or increasing orthopedic soft tissue, like tendons or ligaments, or in the bottom left corner, looking at increased vascular endothelialization or decreased bacteria attachment on catheters. What we have found and what intrigued us about OPM's PEKK material is nanostructured surfaces can control cell responses. And we have seen, a lot of examples of where nanostructured surfaces on different materials can reduce bacteria attachment, can inhibit inflammation, scar tissue growth, and ultimately can increase tissue growth, like bone growth, for example, as highlighted on this slide. So clearly PEKK is one of these, very fascinating nanostructured materials that, personally I wanted to get my hands on and test and see what kind of properties this new chemistry possesses. So next slide, Jim. So as an example for PEKK, here's some of our bacteria results that Jim was referring to before that we have published. We, like many groups, have been looking at non-antibiotic strategies to reduce bacteria colonization. And I think, as everybody knows, I know we're in a current pandemic with COVID-19, but the CDC has predicted further healthcare problems due to the emergence of antibiotic-resistant bacteria. In fact, by 2050, the CDC has predicted more people will die from antibiotic-resistant bacteria than all cancers combined, right? I mean, that's a startling statistic that should make us all think about developing surfaces of orthopedic implants that can reduce bacteria function without resorting to antibiotic use. So clearly, as we have seen, and I'll show some of these results here in terms of colony forming unit assays, that bacteria attachment and growth is much less inhibited on PEKK compared to PEEK, which is in blue on this slide, and titanium, which is in gray. And the y-axis on this slide are the number of colony forming units for one particular bacteria called Staphylococcus epidermidis. This is the bacteria on your skin that commonly infects orthopedic implants. And we have seen upwards of 7 days of reduction in Staphylococcus epidermidis colonization on PEKK, simply because of its chemistry, because of its nanostructured features, because of its inherent properties, not requiring an antibiotic or the release of an antibiotic. And these are in vitro results. So Jim, the next slide really tells the familiar story that we are seeing on these materials. Same graph outline, same color code for the materials where PEKK is in yellow, but here we're studying Pseudomonas aeruginosa, another type of bacteria that infects orthopedic implants, and we're seeing the same proactive bacteria inhibition upwards of 7 days in culture, again, without the use of an antibiotic. And I would also mention this result is incredibly promising to me as a researcher, because now we have looked at gram-positive and gram-negative bacteria. There are two types of bacteria that can infect your implant, and many times you need different antibiotics for those different bacteria. But here we have the same surface in PEKK that is reducing colonization of these two types of bacteria. So next. And the third type of bacteria that we have been looking at is MRSA. Of course, MRSA is the methicillin-resistant version of Staphylococcus aureus. So methicillin is an antibiotic, and this is a great example of why I think in the field we need to move beyond antibiotics as a way to treat orthopedic implant infections, because we created MRSA through our use of the antibiotic methicillin. And it's proven to be quite a hard bacteria to reduce colonization on an orthopedic implant, but the same exact results that we're seeing on PEKK as what I described for Pseudomonas and Staphylococci, a reduction on PEKK without the use of antibiotics upwards of 7 days in culture. So next, we just quickly summarize some of these results from the bacteria portion that we're seeing reduced bacteria colonization. We see the best response actually on MRSA, the antibiotic resistant version. So very promising properties. And now we've started looking into why. Why are these surfaces reducing bacteria colonization? So you can see on this slide, I've highlighted some reasons why nanotextured surfaces seem to be working in medical devices. In the upper left, you can see that natural structures like the insect wing, the surface of an insect wing has nanostructured features. So just emulating those nanostructured features in medical devices can improve an antibacterial response. On the upper right, we've done some work with finite element analysis, looking at that bacteria, which is red in that figure. How does the membrane adapt to nanostructured features? And what we find out is it doesn't adapt to nanostructured features. The bacteria membrane is a little too stiff to fit into those contours, and we don't get a good attachment of bacteria. So through biophysical models, you can explain this behavior. The last reason is shown right in the middle of the slide, and that is that these nanotextures have different surface energy, and that results in different protein absorption to repel bacteria. So on nanostructured features, you have altered protein absorption, altered protein bioactivity, which can keep an implant from being infected. So now, Jim, for the next slide, the specific results we're seeing on PEKK is when we measure its surface energy, as you can see in this table, the surface energy of PEKK is actually closer to 3 proteins in your body that have a natural ability to reduce bacteria colonization. Those 3 proteins, as you can see on the table, casein, mucin, and lubricin. If you can get these 3 proteins to absorb to your implant, you can reduce bacteria colonization. So the chemistry of PEKK, the surface topography of PEKK, gives it a surface energy that's closer to these great proteins in your body that naturally resist bacteria colonization. So the next slide really shows where we've seen, in fact, increased absorption of these proteins in vitro on PEKK compared to titanium and PEKK. In other words, PEKK has that surface energy to increase the absorption of these proteins, and through ELISA assays that we've completed in the lab, we're seeing 5 times, 6 times more absorption of these great proteins on PEKK compared to other materials. Next slide. And the last part of this bacteria story is we've correlated that increased absorption of casein, mucin, and lubricin to decreased bacteria colonization. So we coated these materials, PEKK, titanium, and PEKK, with casein on this slide, and then we allowed Staphylococcus epidermidis to absorb, and they're reduced. Same with Pseudomonas aeruginosa, correlating this increased absorption of casein on PEKK to decrease Pseudomonas colonization. And the last one, MRSA, and all the other proteins and on the samples, we have correlated that increased absorption to decrease bacteria colonization. So the summary on the next slide basically highlights this mechanism of action, that PEKK has the chemistry, has the roughness to absorb 3 key proteins in your body that are known to reduce bacteria colonization. That is the mechanism of action, not related to an antibiotic, not related to releasing reactive oxygen species or any other mechanism that people are looking for other materials. And the last part of what I wanted to share with you, Jim, the next slide, is this mechanism for greater osteointegration that Jim had talked about, this wonderful improved bone growth that you're seeing on PEKK compared to other materials. So the next slide is we, of course, determined in vitro that more bone cells attach to PEKK. And if you get more cells to attach, then more cells will grow, and then more bone will form. So clearly we're seeing greater amounts of bone cell attachment on PEKK compared to these other materials. The next slide, Jim, that is leading to greater mineralization. So a bone cell secretes calcium, secretes bone-related proteins. That is bone, and we call that mineralization, where again, you can see greater amounts of mineralization by osteoblasts, the formation of bone in vitro on PEKK compared to these other materials, PEKK and titanium. So the next slide is really, again, this question of why. Why is this happening? And we go back to the proteins because we see this unique surface energy of PEKK, which is matching the surface energy also of other proteins. And these proteins are known to improve bone cell response. So those proteins are vitronectin, fibronectin, laminin. These proteins are great for promoting bone cell attachment, which we saw, and greater bone formation, mineralization. So we're seeing PEKK has a greater tendency to absorb those proteins, as well as what I mentioned before, the antibacterial proteins, to create for a more antibacterial and more pro-bone growing surface. So this is, I think, is the last data slide that I'll show you that is correlating this increased adsorption of calcium that we're seeing, this increased protein absorption of vitronectin, fibronectin, and laminin, key proteins in your blood that promote bone growth if they absorb to an implant. And those osteoblast adhesion numbers are much greater when we pre-coat PEKK with these proteins and calcium. So again, correlating that if PEKK is absorbing more of those proteins, once they're absorbed, they're promoting bone cell attachment. So next is just the overall summary that we're seeing on PEKK materials when we look at these mechanism of actions, that we're seeing greater initial bone cell attachment, greater bone cell growth in terms of mineralization and extracellular matrix synthesis. And it's related to the unique chemistry, surface roughness of PEKK that is absorbing key proteins in vitro immediately after implantation that is providing antibacterial and pro-bone growing properties. And I think that's it for our recent results, Jim.
Great. Thank you so much, Tom. It was great. So thank you, everybody, for attending the presentation. Appreciate your time. There is a lot of information that we couldn't go through today, so please feel free to stop by our booth in the exhibitor hall, virtual hall. There's a lot more information there and people standing by to answer any kind of questions you may have. And with that, I'll offer up time for questions. Thank you.